Okay, so I've already started redrawing this one. This is problem A here. Draw as many resonance structures as you can for the following species. I drew this out as the condensed structure here with the hydrogen atoms and the carbon atoms explicitly shown. Your book seems to go back and forth between these condensed structures and the skeletal structures. But let's try to stick with the skeletal structure. So here's the skeletal structure. And you don't have to have the CH2 here. You can just draw this as a line ending with a, we know that there's a carbon here, and since there's a lone pair and a negative charge on this carbon, we know that that must be CH2 there. So if this isn't obvious to you, it will be with more and more practice. So let's draw a resonance structure. Well, we have a lone pair. So this is a lone pair next to, and when I say next to, I mean on the carbon next to the carbon. It doesn't matter, it doesn't have to be a carbon, but on the atom, the lone pair is on the atom next to the atom where the pi bond starts. So lone pair on an atom next to a pi bond where the pi bonds start, on next to the atom where the pi bond starts. That is a perfect scenario for drawing a resonance structure. So let's draw the resonance arrows here. So we'll draw a curved arrow going from here to here. Now we know that there's going to be a new pi bond. We're going to lose this lone pair and this negative charge, but that means we have to make room for this pair of electrons going into this pi bond by putting these pi electrons into a new lone pair on oxygen. So if we do that, then we will draw the double-headed arrow here. And now we have 3 lone pairs on oxygen and the negative formal charge. Notice that we had a negative charge in this species here. We had a negative formal charge on this carbon, so this whole molecule has a negative charge. We have to conserve that negative charge, and it has to go somewhere. It ends up on oxygen because oxygen now has the 3 lone pairs and a single bond, and that's the scenario where oxygen has a negative formal charge. So let's look at B. B, we have we don't have to draw the hydrogens here. It kind of helps. It's maybe good practice just to put them in, just to see them so you don't get confused. Let's draw as many resonance forms as we can. So again, a lone pair next to a pi bond. We can't do anything on this side of the molecule. This lone pair can't come in here because there's no place for these electrons to go. The only thing that could happen here would be something like this. If we put that lone pair down here, and this is why the author put in these 2 hydrogens, because you don't want to sort of lose sight of the fact that these 2 hydrogens are here. That will give you 5 bonds to this carbon. So this is a bad resonance structure, and that makes this a bad arrow. So I'm just going to see if I can go back and get rid of this and get rid of that arrow. And now let's look at the other side of the molecule. We have a lone pair next to a pi bond, so let's just put this lone pair, I can just draw it from the negative charge, that's fine too. Put it right here. And now we can put this pi bond onto this carbon. So notice that there's a lone pair going to a pi bond, and now a pi bond going to a lone pair. And let's see what we get when we do that. So we have this new pi bond here, and now the lone pair here on this carbon. And let's not forget the other double bond. So I'll draw in these 2 hydrogens again, just because they're there. Put this one in. Why not? We don't have to. And can you draw another resonance structure? Well, notice that we have another situation where we have a lone pair next to a pi bond. So we can do the same thing here. We can put this lone pair there, and then put this pi bond onto this carbon. And if we do that, and I'm out of room on the right side, so I'll just draw it down here. And now we have this, and I'll just draw these in again. So now we've put in a new pi bond here. This is where the new pi bond is, because this lone pair came in to form this pi bond, and then this pi bond moves out of the way to form the lone pair on this carbon. So these are the three resonance structures that we can draw here. Okay, so let's look at one more, and then I'll let you do the rest on your own. So C is what we call guanidinium. And I will do this as a skeletal structure. And I'm going to draw it in a different way here that's more realistic, more appropriate to the geometry of the molecule. So I'm just going to sort of rotate this molecule right here. And notice that this is the same thing as what's drawn in C. So this is guanidinium. It's also it's part of the molecule arginine. Part of arginine. It's called guanidinium. Guanidinium. Arginine is one of the 20 natural amino acids, so it's a very important molecule. Now, it will really help if we draw in all the lone pairs, and the lone pairs are shown for you here in the molecule, sorry, there and there, so we'll draw those in. And we didn't draw the carbon atom because we don't have to in a skeletal structure. And we drew it more as a trigonal planar structure, which is what it is, because this carbon is sp2 hybridized in the middle. So this is not a very well-drawn structure because it suggests that these bonds are coming out at 90-degree angles, which is one of the problems I have with this textbook. I think they just do these types of structures out of convenience because maybe it's just easier to typeset that way. But so now that we have our realistically drawn structure, let's see what we can do. Well, again, the same scenario where we have a lone pair next to a pi bond, So either of these lone pairs can participate in the resonance with this pi bond. And notice this pi bond could then go on to nitrogen. Let's see what happens if we do that. Let's just start from this lone pair right here into that, making a new pi bond, and then this pi bond making room, going on to the atom that is the second atom of the pi bond. So notice that we did the same thing here. We put the lone pair into the new pi bond, and then the pi bond moved over onto, both of these electrons moved onto this carbon right here, and you went from a pair of electrons in a pi bond to a pair of electrons localized onto that carbon. Here we have a pair of electrons in this lone pair going into a new pi bond, and then this pair of electrons in this pi bond being localized onto nitrogen. So what does that give us? That gives us a new resonance structure here. Now, notice that the hydrogens don't change. We don't move protons around. We don't move nuclei around. We're only moving electrons. So in this case, since we moved these two electrons into this pi bond, now you should very quickly notice that the formal charges will change. Here, now nitrogen has 4 bonds, H2, and then these 2 bonds here. So you should quickly just see that that has to have a plus formal charge. And now this nitrogen has 3 bonds, 2 to the hydrogens and 1 single bond to this carbon. So now this is where the lone pair ends up, and it has no formal charge. And then this lone pair is here. So now we do it again with this. Actually, I'm going to make a little bit more room. So we can do it again, where we could have started with this pair of electrons on this side, but now that we're here, we can move this pair of electrons in to this pi bond to make this new pi bond, and then this pair of electrons go onto that nitrogen, and we get this structure. And all of these remain NH2. The protons don't move, but now we have a plus formal charge on this nitrogen. So notice what happened. This lone pair now moved here, and this moved onto this nitrogen. We also could have gone from here, we could have gone from this resonance structure, this one here, directly to this one. And it doesn't matter what order you start, or where you start, or what order you go in. The lone pair, the arrows are just showing how you move the electrons to get from one resonance structure to another. So if we had drawn the arrows like this, so here's the first structure that we started out with. If we had drawn the arrows like this from here, we would have ended up with this structure, NH2 with the double bond there. So notice that this is the same as this, which indicates that there's no particular order that you have to go in. We just described the 3 resonance structures. So this and this are the same thing. So there are 3, 1, 2, 1, 2, 3, and this is the same. So we'll call that 3. We've drawn all of the resonance structures of guanidinium, and the nice thing about the resonance approach is that with these 3 resonance structures, with these 3 unique Lewis structures, we can see that this positive charge is shared among all 3 nitrogen atoms. And that's indeed the case. All of these bonds are in the real guanidinium. All of the bonds to nitrogen are of the same length, and you have a partial positive charge here, and it's a third, a third, and a third. So a third of a positive charge on each of these nitrogens. And then the pi electrons, you can just say, are delocalized around here, which is why we don't usually draw the structure like this, because it's a little awkward to show how those pi electrons are distributed. This is why we have to resort to resonance to indicate. It says the same thing. It says that the positive charge is delocalized among all 3 nitrogen atoms, and that the pi electrons are also delocalized.